Hi everyone, I'm Shouvik. I am an Institute Postdoctoral Fellow at the Indian Institute of Technology, Bombay, and I would like to thank the organizers for uh, giving me the opportunity to present my work at this workshop. I'll now start my presentation. I'll present the results from my recent work with Steen Hannestad and Thomas Tram from Aarhus University, Denmark, on strong massive neutrino self-interactions and the Hubble tension. My talk is based on this recent paper, Updated Constraints on Massive Neutrino Self-Interactions from Cosmology in Light of the H-Naught Tension, which has been accepted in Journal of Cosmology and Astroparticle Physics. Let me start by introducing neutrinos. Active neutrinos have three mass eigenstates, which are quantum superpositions of three flavor eigenstates: the electron neutrino, muon neutrino, and the tau neutrino. Tightest bounds on the sum of these neutrino masses come from cosmology. In our work, we use the degenerate mass approximation where all the masses are considered equal, and this works well for the current cosmological data. Here we introduce an additional parameter, n effective, to parameterize the effective number of relativistic degrees of freedom other than photons in the early universe. In our paper, we have updated the constraints from cosmological data on flavor universal neutrino self-interactions mediated by a heavy scalar of allowed mass higher than 1 keV, so as to be able to treat the neutrino self-interactions as an effective 4-5 muon interaction for the modes probed by current Planck CMB data. A heavy vector mediator also works. We consider a simplified interaction with diagonal coupling matrix as shown in the slide. The effective self-coupling, G effective, as long as this effective self-coupling is greater than the Fermi constant, the neutrinos will remain interacting with each other even after decoupling from the photons at the temperature of 1 mega electron volts. The self-interaction rate per particle gamma is proportional to G effective squared multiplied by T nu to the power 5, where T nu is the neutrino temperature. So this interaction will stop neutrinos from free streaming as long as gamma is greater than H. So introducing this kind of interaction among neutrinos had shown potential in solving the Hubble tension in the earlier works in very strong interaction range, where the coupling strength is 10 to the power 9 times that one from the weak interactions. This prevents neutrinos from free streaming even until matter radiation equality. The cosmological model of interest here is an extended lambda CDM model with three additional parameters: n effective, sum of neutron masses, and the log of the coupling strength, G effective. We work in the units of MeV to the power minus 2. So uh, the argument in the log doesn't have an unit. Since neutrino self-interactions delay neutrino free streaming, this causes a change in the gravitational potential, which in turn affects the photon perturbations. You can see the effect of large interaction like G effective equal to 10 to the minus 2 MeV to the power minus 2 via the solid red curve in the plots. Strong interactions gradually add more and more power in the higher multipoles of the CMB temperature spectra. It also causes a phase shift of the CMB anisotropy peaks towards the smaller scales. However, if N effective is increased to 4.046 from the standard value of 3.046, we see that the changes due to the high G effective is almost compensated in that dotted red curve in the lowermost panel. Increasing neutrino masses from 0.06 eV to 0.23 eV also causes small compensation towards the changes made by a high G effective value, as can be seen from the middle panel dotted red curve. So using this model, in the strong interaction range, Kreis et al. Had found a region of allowed parameter space with high G effective values accompanied with high ineffective sum of neutron masses and H naught with Planck 2015 low multipole and high multipole temperature along with lensing data combined with BAO. And they got similar goodness of fit to the data as lambda CDM. So uh, they don't use the polarization data in their main results, but in this model, N effective and H naught are positively correlated, and the solution to the Hubble tension came from high ineffective values. Apart from the strongly interacting mode, another interacting mode is found at log G effective less than -2 with a plateau in between the two modes where the posterior diminishes to 0. So this model thus had drawn a lot of interest in the cosmology community due to its potential to solve the Hubble tension in the strong interaction regime of log G effective greater than -2. With the public release of the final Planck 2018 likelihoods, we thought it is timely to test this model against the new Planck likelihoods. So here I briefly describe the lambda CDM parameterization, which has 6 model parameters. The small omega c and omega b are the present day physical cold dark matter and baryon densities. Theta mc is the parameter used by Cosmo MC to parameterize the angular size of the sound horizon at decoupling. Tau is the optical depth to reionization, which is line of sight integral of the number density of free electrons multiplied by Thomson scattering cross section. NS and AS are the power law spectral index and amplitude of the primordial curvature perturbations, respectively, defined at the pivot scale of k star equal to 0.05 H MPC inverse. So we use flat priors on these parameters in the model as shown in this slide. So we are using a flat prior on log G effective instead of G effective because we want to probe orders of magnitude of the parameter range in G effective. Now I come to our analysis method. We use the nested sampler polychord combined with Cosmo MC, aka Cosmochord, and this uh, uh, special thanks to Will Handley for this, for making it publicly available. So since the posterior distribution is bimodal, a nested sampling package like Polychord allows us to properly sample the parameter space and also to calculate Bayesian evidence. Me and my collaborators modify the CAMP code to incorporate the Neutrino Self-interactions in the perturbation equations. We first sample the parameter space using the full prior range of log G effective, which is from -5.5 to -0.1. And this is what we considered. For this, we use 4,000 live points and an advanced boost posterior settings to ensure that the obtained bimodal posterior distributions are accurate. This, of course, required a huge amount of computational power. To obtain parameter constraints for the individual interaction modes, we also divided log G effective parameter space in the moderately interacting range, denoted MI nu, and the strongly interacting range denoted SI nu. So we run this analysis separately using 2000 light points, since when we have already divided the parameter space, the posteriors will be unimodal, hence a less computationally demanding setting. We also run the non-interacting scenario denoted by NI nu. So in the NI nu case, we do not have the log G effective parameter. Among datasets, we denote the Planck 2018 low L and high L temperature data as TT. When we add the high L, TE, and EE power spectra to TT, we denote this as TT, TE, EE. We denote the low L E mode polarization data as low E. So apart from that, we combine additional data sets into this notation EXT, where EXT contains Planck 2018 CMB lensing, BAO measurements from MGS 60 FGS and SDSS 3 BOS DR12, RSG measurements again from BOS TR12, and uncalibrated type 1 is supernova luminosity distance measurements from the Pantheon sample. In some runs, we also use a Gaussian prior from on the Hubble constant from Rees et al.'s 2019 measurement, which is 74.03 plus minus 1.42 kilometer per second per MPC. That is at 4.4 sigma tension with Planck 2018 in lambda CDM model. So this value from Rees et al. Has changed to 73.2 plus minus 1.3 kilometers per second per MPC in 2020. So here we want to emphasize that for a model to be acceptable solution to the Hubble tension, it has to provide H naught values close to 73 kilometer per second per MPC using the full Planck data combined with other cosmological data sets, but without using the R19 prior. So in this slide, we show the 1D posterior distribution of various parameters for the runs using the full prior range of log G effective. In the lower left, you can see that the log G effective posterior for all the dataset combinations leads to a two-mode posterior. In the upper left, one can see that the strongly interacting mode also leads to a completely separate region for theta MC. So now if you consider the two plots at the right, they correspond to N effective and H naught. And you can see that with TT plus low E data, that is the uh, black curve, a very large region in the N effective and H naught parameter space is allowed, and there is no conflict with the shoes measurement. However, as soon as we add the high L polarizing data, the high N effective and H naught values are discarded. With the inclusion of the additional EXT data, the allowed parameter space gets slightly narrower. Thus, as you can see with our most constraining data set, TTT plus low E plus EXT, we do not solve the Hubble tension in this model. So in this slide, we show the 1D posterior probability plots for runs where we had separated the moderately and the strongly interacting modes. The red and green curves correspond to the strongly interacting mode, whereas the blue and black curves correspond to the moderately interacting mode. You can see that the strongly interacting mode also prefers a high theta MC and low NS values. This is because the changes in the amplitude and the phase shift in the CMB peaks can be partially compensated by decreasing NS and increasing theta MC. Interestingly, as far as N effective and H naught go, the SI new mode or strongly interacting mode actually prefers slightly lower values of N effective and H naught than the MI new mode when this polarization data is included. Although there is no conceivable tension between the moderately interacting and strongly interacting modes regarding N effective and H naught values. Now, in this slide, we show the 68 and 95% 2D correlation plots between various parameters. From the upper right plot, we can see that the N effective and the H naught are strongly correlated in this model. And since N effective is strongly constrained by the high L polarization data, high values of H naught that can solve the Hubble tension get discarded as well. So this uh, being not able to solve the Hubble tension is related to the polarization data. So to summarize, log G effective is degenerate with theta MC and NS, and this allows for a bimodal posterior distribution even with the latest full Planck likelihoods. In the CMB-TT data, the log G effective has also some degeneracy with N effective and some of neutrino masses. This allows for high N effective values close to 4 and high H naught values around 73, 74, as long as the high L polarization data is not included. Once the high L polarization data is included, it constrains N effective heavily and does not allow for high H naught values that can reconcile CMB with shoes measurement. with TTTEE plus low E plus EXT, we found that for strongly interacting mode, the following 95% bounds on screen, and you see that H naught is uh, same as for the case for lambda CDM model. N effective is like at the slightly lower side at 2.73 plus 73 plus minus zero point 0.3, but this includes the lambda CDM value. And sum of neutrino masses is less than 0.15 eV. So we have an upper bound, which is consistent with the lambda CDM model, which gives an upper bound of 0.12 eV. The as I said, the preferred ineffective values are slightly on the lower side compared to the lambda CDM value of 3.044. So, but even if we were to reanalyze the data with uh, fixed N effective of 3.044, massive neutrinos, uh, one would one would very likely get an H naught in the ballpark of around 69 to 70 kilometer per second per MPC, which does not work as a solution to the Hubble tension, even though it reduces the tension to some extent. Furthermore, neutrino self-interactions are also strongly constrained from particle physics experiments, with the exception of flavor-specific interaction among the tau neutrinos, introducing the interaction realistically to only one flavor would provide an even smaller increment to H naught, as the effect on the CMB power spectra would be smaller due to G effect in only one species of neutrinos. Now, coming to the goodness of it, we found that the with TTTEE plus low E plus EXT dataset, a best fit chi-square difference of around 3.4 between the strongly interacting and the non-interacting mode, and also a Bayesian evidence ratio of 0.06. So both statistics disfavor the strong interaction scenario when compared to the non-interacting case. However, the moderately interacting mode gives similar fit to the non-interacting case and also almost similar parameter constraints. The reason is that for the moderate coupling strength region, the neutrinos start free streaming too early as far as the Planck CMB measurements are concerned. So I'll conclude with the remark that with current data, this model does not look like a promising solution to the H naught discrepancy. So thanks a lot for listening, and your questions are welcome.